Thank you all. It's a real pleasure to be here. And I also appreciate the organizers. I'm going a little bit out of order because of some flight challenges. So thank you all very much. Uh, Briefly, by disclosure, I'm a stockholder and consultant to Synchron. So take that for what it's worth. So this is something you're going to get a lot of later today, but for 20 years, BCI has been incredibly promising, starting with Lee Hockford's publication in 2006 in Nature with a Utah array directly sort of going through the PIA and reading cell signals. There's been tremendous progress with incredible abilities to do things, manipulate arms and hands, and do very complex movements. And most recently in 2023, a really amazing paper by the UCSF group using an Icahn array to be able to generate language from electrocortical signals. So there's been all this fantastic stuff. This is the paper from 2016 from Van Stiesel, which really set the stage in terms of our thinking because it was the first implantable sort of BCI system. So it was a grid array that was fully implanted, didn't have wires coming out, transmitted through a pocket. This was published in the New England Journal. And it basically allowed the patient to take this complex technology and use it at home in a meaningful way. She could use it outside where eye tracking didn't work and other things. And in fact, even 43 months later, this is the patient who shared that her eyes had become too slow for eye tracking at all. If she didn't have the implantable BCI, she wouldn't have any words. So it gives you a highlight of how incredibly powerful this technology can be. Patients with severe motor impairment, what they want is a return of autonomy. They want the ability to control their lives. You don't realize how little they have when they're missing
Beautiful.
that. These are a few quotes that sort of help
section.
bring it. First, these are not from patients, but from the
Very
outside.
happy.
You know, in Van Stiesel's paper, a BCI to be meaningful in the real world, it must allow for user autonomy, continuous functionality, not be something that's done in a laboratory. And likewise, at the International Classification of Functioning Disability and Death, autonomy is sort of described as the ability to make choices and have control over your environment. And these are some patients and caregivers of ALS patients who share kind of how incredible it is. Like you think about it, you know, he'd lie there for 3 hours just staring. He can't get help, can't do anything unless someone comes. You know, there are reports of caregivers sort of punishing their patients by turning the eye tracker so that the patient can't communicate. There's nothing they can do. There's no privacy. There's no ability to control when and how they do things except for at the whim of other people. And this is what we hope to change. So fundamentals for BCI use in the real world is that it's immediate, it's easy to learn, it's not complicated, it's stable and reliable, and you show over a long time it doesn't degrade, and that it's continuously available for the patient whenever they want, not dependent on someone to set it up or make it work. And so that brings us to our attempt at a solution for that, which is the Stentrode, which is a fully implanted wireless electrocorticography array that's placed into the sagittal sinus at this point. It's very simple. You go transvascularly, deploy the sagittal sinus adjacent to the motor and premotor cortices. It reads the signals of intended movement, what we call brain gestures, thinking of moving your foot or moving your hand, and that transmits to a transmitter here that sends to a decoder that's somewhere within something like 6 meters or something, and then that can receive it and send a Bluetooth signal to any technology at all. And this is just sort of to highlight this. Hopefully the video will play. There you can sort of see. So we're just showing, you're just unsheathing a stent. This is something that neurointerventionalists do all the time. It's a very simple procedure. It's not incredibly complex. You don't need unwieldy equipment or special robots to make it work. And this is just to compare and it didn't work right. But that video was intended to show you deploying a stent in an MCA, which is done over 25,000 times a year, and deploying a stent in the sagittal sinus. There's no big difference. Likewise, there are over 300,000 coronary pockets, subcutaneous pockets placed. There are over 60,000 neuro pockets placed per year. These are routine procedures that are done all the time. There are over 2,500 neurointerventionalists in the country. So there's an ample workforce. It's a workforce that's desperate for elective procedures because they're doing so much stroke call. So there's a ready and able and willing environment for this technology to become immediately available. So the concept is we read the signal in the brain thinks of a gesture, it picks it up. Normally, that goes through your normal process to make your muscle move and touch your screen. What we do instead is read it and then send a Bluetooth signal out to allow you to touch your screen and interact with your digital world. This is a video of our last patient in the last trial for getting hooked up for the first time. And it's just really cool because you can see how emotional it is when this is the very first time he gets hooked up and he's able to use his brain to make the clicks. And it's really, he's recognizing this is going to change his life. And here are just a few examples. This is early. This is the very first patient on your left. I love this video. This is the very first time it's been used. I don't know if it's going to play right, but basically he's just using it on Bluetooth. Now, here's more recent. This gentleman, as you can see, he's at home, but he's in a hospital bed. He's completely compromised. He can't do anything. He can't even do eye tracking. He has a little bit of facial twitch. That's all. He's using the Synchron brain computer interface to communicate to his caregiver that he has abdominal pain and how much that pain is. And in the process of doing that, it's really quite striking. And hopefully it'll happen here. You'll see once he sends the message, he makes this little smile, and it always kind of gets me in the gut to see it because it's almost like a little baby or something. But you can see the joy and sort of the excitement that he feels that he's able to do this independently, which is really touching. And then we're advancing to do other things. So now the original device, the first trial that we did in Australia, a person could get sort of a singular click. Now we can vary intensity of click. So this is training where they're given a target, and based on how they think the thought, that one brain gesture can give multiple tiers of intensity of response. So it gives you the ability to do different things with that. And this will allow them to then do all of these important activities that almost all of us do at home digitally already, or in my case, my wife does them all for me. But this is the reality. This is what we use. This is how we interact with our world now. So here's an interesting example where we're using ChatGPT in an iOS system to drive improved communication, where we're now getting 20 words plus a minute, because the doc, he gets a message, "Are you awake?" He's able to go through and choose which one he wants to use, and then get that answer back, and then he sends it, and then someone will respond, what they think and such. And then also we've been working with the I forget what it's called, the Apple Oculus Eye thing. I can't believe I forgot all of a sudden. But it's interesting. You can see he's playing cards. The woman who's not paralyzed, they use hand gestures to make it work, whereas he's using the Synchron to make it work for his clicking and moving and choosing the cards and such, which is pretty cool. So here are the results. This is our initial trial, which is published. The switch trial, 4 patients implanted in Australia, no SAEs or device migration or vessel occlusion. The primary endpoint, which is the same in both of the feasibility trials, are device-related SAEs. Sorry, it's not no SAEs at all. It's SAEs that are device-related, resulting in death or permanently increased disability. Also, no evidence of stenosis, no evidence of stroke, no evidence of stent migration. So the technical aspects of the procedure are incredibly safe. JAMA Neurology, this was published. The COMMAND trial, we're waiting for the last follow-up, but all of the patients have been enrolled. They were done at UPMC, Buffalo, and New York City. Again, primary safety endpoint, no patients met the primary safety endpoint. Actually, I can update that. That's 0 of 5 now, not 0 of 2. There's only 1 patient waiting for their 12-month, and no instance of device migration, thrombosis, or stenosis. And this is just the beginning, because right now we're doing sort of very basic, put it in the sagittal sinus and read this area. But the vasculature, as many of you know, give us access to all areas of the brain. You can go into petrosal sinuses, cortical veins, and many other structures to access all kinds of other eloquent regions, which we're very excited for. So in summary, I think there's a couple of critical things about what makes this technology so exciting and such a great opportunity. Number one, you're leveraging a neurovascular experience that's incredibly widely available. The workforce is growing extremely quickly. The SNIS every single year sets new membership records, and they're very much seeking increased elective volume to supplement the emergency burden of care. The technical requirements are very very low. These are things that we do every single day, all the time, day in, day out. They're regular type things. There's nothing complicated. You don't need a giant team of neurophysiologists to work through the process of what you're doing. It's immediately available. It's very easy to use. It's immediately able to be brought to the home. All of these cases, all of these things are done in home. Patients don't have to come to a laboratory. They don't have to use complicated things. And we have data now. I wanted to include, I didn't get a chance to put it in, but we have long-term stability data that shows, in fact, we have one of the Australian patients still using the device. We're now at like 6 years. He's still able to use the device very regularly, very consistently, 5 years. Without any degradation. You know, just like the stents we've been putting into vessels for forever. If any of you have done surgery on a patient that has a prior aneurysm, and a couple shots of patients that I've gone back in for aneurysms with pipelines or stents, and what do? You see the stent and it's in the outside adventitia of the vessel always. You can see it right there, but there's no inflammation in the brain. There's no scarring. There's no anything. And so what happens is, as it engrafts, you get better signaling over time, over the first month or two. And then once it's stable in there, it's just there and it's part of you. There's no long-term degradation. There's no gliosis or any of these issues. The technology is continuously available. In the current iteration, we have to put the first-in-man version of the technology. We had to put a little battery. It needed a separate power source that we had to sort of magnetically tape to the chest. That's what you saw that woman doing. The commercial version, which is going to be available in Q1 of this year, does not require that. It has its own internal battery and can be just charged like an Apple Watch whenever you want. And so the goal is to give digital access and digital interaction and autonomy back to these patients. The goal is essentially to bring BCI from the laboratory experience into the home. And we're very close to doing that. With that, I'll say thank you and happily answer any questions.
Did these have any different antiplatelet or anticoagulant requirements compared to us putting a stent in the MCA or transverse sinus or anything?
No. Double antiplatelet therapy at the physician's choice for 3 months. Stop the second agent. Keep the single agent for as long as you want. It's essentially exactly the same as if we stent for IIH or tinnitus or an MCA aneurysm. It's all the same.
Awesome. Thank you.
Anything else?
What's the biggest misconception about BCI that you hear just from the general public or your colleagues?
I think that this is a debate, and we have some great BCI, other BCI leading companies here that are doing some spectacular stuff that I'm interested in and think is wonderful. But I do think one of the things that people get caught up in is what's your data volume? How much information are you sucking out of the brain? Can we use this to recreate vision or do all these other really sort of sci-fi things, which are cool and wonderful? But I think it's a misconception to think that's what BCI, that's where the need is right now for BCI. With very little information, and I love to use the analogy, for all of you that have kids, or maybe even for you yourselves, I have kids, they play an Xbox. And when they play that Xbox, with very little or even the Switch, the Nintendo Switch, right? It's like an old Nintendo controller. It's like front, back, left, right, and 2 buttons. And with that, they can do like 80 different fight moves and throw fireballs and jump and slide and do all kinds of things, depending on how they use those 6 simple commands. And when they first learn, you think, oh, I have to press A to punch and I have to press B to shoot my fireball or whatever. But as you play it, you don't think that anymore. You think jump, punch, but your brain, as amazing as it is, just rewires for that. And so you don't even think it. They're like, Dad, how come you can't do it? You just go over there and do that. And I just fall off the thing and die. And so I think that that's one of the misconceptions. I don't think BCI needs necessarily hundreds of data outputs. I think that if I can give any number of human beings 6 reliable, long-term, easy to use, immediately always available outputs, they could pretty much do anything that we do right now in the world. And so that would be the thing that I think people get most hung up on. Yes.
Jay, great work. 2 questions. When will the trial be open for us to participate? I'm certainly interested, so please keep me in mind. Number 1. Number 2 is how much patient training does it require before the implant or after implant, how to use the system and things like that? Because different places have different resources. Because for me, it sounds like I need a team to train that patient before and after, et cetera. Could you talk a little bit about that?
Yeah, I love that question. It's like you just tossed it up for me. Almost none. And in fact, that was like something we messed up early on. If I showed you the chart for training sessions from the first trial in Australia, the first patient, it was like 8 sessions till he was using the device. It was because we were doing so much training. And every other patient since, in the first day, they're able to start creating DMOs and doing certain things. Now, the first day they're not doing, the 4 switches that we've had now with the first generation, and hopefully the 8 or 10 that we get with the next one. But they're immediately able to start using it. And part of it was us stepping back, letting them play with it, and letting there's complex AI algorithms that are written into it to recognize the electrical patterns and sort of let the AI run with the patient and figure it out. So with this device and this iteration, the training bar is extremely low. And essentially every patient since the first patient, maybe there's one that took 2 sessions, everybody has been actively using it and creating what we call digital motor output, a DMO, in their first session.
Great talk, thank you. It's a question from an engineer. I'm wondering
That
about...
gets me scared, by the way, when he says that. I'm really just a face guy.
No, it's a biological question so that it doesn't sound too stupid. So I'm wondering about the side effects on blood flow and the blood-brain barrier. We know when we put something in the brain rewires itself around the foreign object. Now, is there a similar phenomena with the blood flow that is sprouting of new blood vessels? How does the brain react to having contacts in?
So this is something we were extremely worried about when we started. So when we started planning this stuff in, I can't remember now, 2015 or so, we didn't know these things. What we've learned, and apropos to one of the earlier questions, at this state, over the last decade, not only have we gained our experience of our 10 patients, but the process and concept of venous stenting has become ubiquitous. So there are tens of thousands of venous stents placed every single year now worldwide, and many thousands in the US. And so we have robust literature and experience around that. And what I'd say is, although this is a brain-computer interface, we're actually brain adjacent, right? We're not violating the PIA. We're not getting into the level of the blood-brain barrier. So we're not creating gliosis or any of those things. We have yet to see any effects. I'm not saying there aren't something, maybe 40 years down the road, there's some kind of venous outflow phenomenon or something. But in 10 patients we have 18 years now of implanted stent across the 10 patients. And we haven't seen any vascular related phenomenon or events identified, not one.
Thank you.
You mentioned access in other parts of cortical veins or other sinuses. For instance, what about language? Is that a possibility on the near horizon that you could park it near Wernicke or Broca's?
I do think so. Yes, I do. I think Wernicke, Broca's, the potential visual, are we going to get the kind of resolution what people are really going to see? That's probably for some higher density data transport technologies. But yeah, I think so. I think there's tremendous potential. And then there's also potential to stimulate seizure management and a number of other things, pain syndromes and other things. So there has been a publication showing that we can use this technology to also stimulate in animal models, not in people.
Fascinating. Well, after watching over the shoulder of my kids for many, many years play COD, I'm glad to hear finally something. I thought for years something good has got to come out of this. So
Exactly.
you reaffirm that. So thank you so much for coming. Came a long way, and we appreciate it. How about a round of applause?
Thank you all very much.